even do that in the first place.
Okay. Good day. Good day, indeed. Good day. Hello. Yes. Awesome. Okay. Ah, yes. I like this class. Right. Okay. Good day. Good afternoon. Good afternoon. Good day. Hello, indeed. I think. All right. We're just so I think you can hear me. I think you can see, like, and tell me if you can't, the board where we left off. I'm just gonna keep we got to get to the stuff. We're almost running at the ground, but we're still trying to hit the ground with this. So I'm just going to keep going from where we were Tuesday, if you don't mind. I'm going over the homework 1, which I still have to get back to, and all of that. And there isn't opportunity for homework 2 until we get through this. But okay, I still haven't also told you how this has to do with the new physics, or what the new physics is. Technically, everything we've said so far about homework 1, or on this board that's still left me, technically everything we've said so far has come from material of physics 1, which doesn't at all mean that it's assumed that everybody remembers it, but like in terms of the history of physics, all these ideas that we've said so far are still like Newtonian ideas about points of mass moving through points of space throughout points of time. Okay. Now, remember our goal now, we still have the same physics concern as always. We're still looking at stuff in space and time. And we're still just trying to make a prediction. Where is this mass going to be 1 second into this type of motion? And the type of motion is springy motion. But we're about to hit a mathematical, oh, did I assign you? God, I don't even remember if I can't even remember if I posted it or not, but we're about to hit a mathematical thing that that was new at the time it was hit historically in physics. So it's new to us in the same way. And just like new math gets invented every day from old math, i.e. human brains, like they go the next step and they're not just pulling the new math out of nowhere. Same thing here, we're going to go the next step and develop it ourselves and continually thereby try to reconvince ourselves that all this physics and math actually does like make sense, and it's not just, it's not only for geniuses to understand. It might sometimes only be for geniuses to fully believe in and invent. But anyway, we're at this stage now where we're saying I'm about to turn the page. Well, I am going to turn the page. Like we left off here. What we're looking for, to remind everybody, we're looking for love in all the wrong places. No. We're looking. So sorry. We're looking for X. right? We're good old typical physics. We're looking for position as a function of time. We're looking for some equation. We are looking for some relationship equation between time and space that tells us, okay, if you plug in a certain number of seconds, we'll be able to tell you exactly how many meters or centimeters this mass has traveled in that time. Like, and we're talking about this mass in the thing on a spring situation. Like, we're looking for that equation. If we were students and we didn't know that this could be done, we would think that we're looking in books or on the web for the equation that already exists. And like, maybe we even did that when we were trying to do this homework. And there's nothing illegal about that. But recognize that even if we find the equation for this on the web or in a book, it got there because somebody realized that it made sense and was able to think it through on their own. So we can too. So in other words, we're looking for an x equals function of t such that, and I'm going to turn back the page for a second, such that this physics that was circled at the bottom is satisfied, right? So I'm going to go one step further. I'm going to take that equation. I'm going to divide both sides by m just to make it super clear what's going on. I'm going to take this equation at the bottom and I'm going to divide both sides. I mean, I'm not saying there's a big deal, but I just don't want to throw anybody off. Like, that's the step that we ended up with 2 days ago. We're going to divide both sides by m, okay, so that what I'm going to write down, so as far as I'm concerned now, and I'm going to flip the left side with the right side. So what we have is, okay, now I intentionally put the m under the k like that. I could have put it under the kx, like I could say kx all over m, but I'm intentionally putting the k and m together in parentheses to stress the fact that they're both letters, right? K and m are both letters, but they're letters that stand for constants. They're letters because they stand for any number we want. Like, it could be any spring, whatever we're saying here could apply to any spring in a lab. Your spring of a stiffness of 100 meters per meter, or my spring, which has a more stiffness of 200 newtons per meter. It won't matter what the K is. That's why K is left as a general letter. And similarly, whatever we're saying here is going to be true of any mass. So we leave it as a letter, not a number. But I have to stress, because these letters, in fact, let me stress right now, these letters right here, even though they're letters, they're both constants. They are numbers. They are functioning as steady numbers that would not change throughout the analysis of this equation, just numbers that we happen not to have specified, okay? As opposed to x and t, right? I've been trying to do this. X and t are not constants. They are letters serving a different purpose. X and t are variables, right? And one of them is the independent variable, one of them is the dependent variable. And that makes a difference. It's going to make a big difference in a moment. T is the independent variable. We're plotting everything with respect to time. And x is the dependent variable. X depends on t, not the other way around. Hold on, just someone in the waiting room, pardon me. Okay. So what we have here, if I write it, like if I write this equation that we got from physics, physics has popped out an equation that looks like this. It's a second derivative on the left side of the equation, and it's a bunch of letters on the right side. This equation is containing the information we want. It's the relationship between the variable x and the variable t. That is what we want, the relationship between those two variables. And the relationship is expressed like by means of these constants k and m. But again, they're just constants, right? They might as well be the number 5 and 3. It's just that it's 5 and 3 in one case, and it's 5 and 300 in another case, and this equation covers both cases. Like, okay, but I'm saying this contains all the information we're looking for, x and t, but it's expressing it in a very ass backwards way, in a very complicated way. What we have here is not saying if you give me a t, put it into my box, I'll spit back at you an x. What this is saying is, if you give me an x, if you give me some value of x, which was the thing we were looking for, if you give me some value of the dependent variable, well, then I could tell you precisely what's going on with the rate of change of that dependent variable with respect to time. Okay, like in other words, This is containing the information we're looking for, but this is totally not what we're looking for. We want x as a function of t. You spit in t as an input, and it will spit out x as an output. That's what we want. What we have here is you spit x in as an input, and you get back out the second derivative of x with respect to t. Same information, but organized in such a different way here that directly speaking, I can't use it. It doesn't answer my question. Like basically, if I'm trying to do the homework and I want to know what is x when t is 1, there's no way I can plug into this thing and find out. So we have math work to do, okay? The math work we have to do is unlock this thing and turn it into a function. What this thing is, sorry. So we need to find an x of t that satisfies this equation that we found. We did find an equation. It's just not the type we're looking for. What we're looking for is a straight up function. What we found is called a differential equation. Okay. As I say, we're still in a building phase here, like building the material that we actually have to navigate through for the course. I mean, as strange as that might sound. But this is this is kind of like the Galileo's principle of relativity kind of thing for physics 1 or something. Like, I want to say we have to deal with differential equations in this course. There's a thing in math called a differential equation, okay? It got stumbled on and discovered because people needed it, because it describes things in nature, i.e. we're coming across it just as physicists in our quest to understand space and time. Now, differential equations are something interesting in math. To put it, my first note here says, note, a differential equation is something more than simply an equation involving a derivative. And I want to make that clear. Like, derivatives are already something everybody's learned in calculus. Some people are comfortable with them, some people are not, whatever. But you have seen equations that have derivatives in them. I have to admit right now, or I have to say with excitement, there are equations that involve derivatives, but then there's a special subcategory of these called differential equations, and they are something a little bit deeper or more interesting than simply just, they involve something more than just the mentioning of a derivative. They are deep and interesting enough that there are entire math classes called differential equations. I had to take 2 different classes called differential equations in graduate school when I studied physics. And so they are a thing, and we're going to stop talking about this thing. We need this thing for physics. But I want to make absolutely clear before I go any further, I don't expect that anybody in this class has taken a class called differential equation. Not only I don't expect it, I definitely don't require it. I don't want it. Like, it was not a prerequisite for this class. So I don't want anybody to get misunderstood. What I want to do is for the same thing with you guys as was done with me, which is we will learn together exactly enough of differential equations that we need to do physics, just like happened to me. In other words, I think math is a lot easier when you do it through physics. I don't think requiring math makes physics easier. I think physics is the way to teach math. So let me start by saying, I don't expect that any of you have actually know anything about differential equations. I don't want you to have known anything. If you happen to, if you've taken a class called differential equations, or if you've studied them on your own, then that's terrific. That's great. And you'll just be even that much faster or better with us here. Fine. But it's not a requirement of anybody. I'm going to now tell you, well, we're here in class, we're going to see what we need to know about them in order to do this physics. And maybe you'll end up actually also getting more about math. I don't know, but that's what happened to me. I mean, I didn't like start off having any interest in math, but so what I'm saying is we have in front of us, we have a differential equation. We're going to solve it. Okay. In order to solve it though, we're going to take a little practice sidebar journey to make sure we're okay with the background math that we need. So here's what I'm saying. Okay, I'm saying this, so you want to know this equation that we just developed is a physics thing. Okay, it's a fancy way of saying Hooke's law. Like this is Hooke's law. Yeah. Okay, what we have here is just Hooke's law in math looking form. I'm saying it's called a differential equation, and I want you to know that before we solve it or whatever, or I want you to know that so that you see why it's going to take us a little time to solve it and why we couldn't have just solved it last semester. Okay, but in order to make a couple of things clear, let me also say this thing okay, this happens to be the type of differential equation that's called a second order differential equation for exactly the reason that you might think, and it's important I say this, like this equation, you notice on the left side, there's a derivative for sure, dx dt, but as you see, I mean, hopefully you can see the board and please tell me if you can't, but on the left-hand side of that equation is a second derivative, right? Like there's no first derivative to be seen at all. The lowest derivative that we see in this equation is a second derivative. That already makes it more hard than it might be. Like that makes it be called a second order differential equation because it's referring to a second derivative. Now, I want to say there's a such thing as a first order differential equation, and I'm going to write one down right now and we're going to look at it. Well, yeah, okay, so I'll show you. So this is a second order, okay? It's what physics is bringing us to in the natural course of thinking. Remember, all we did was pick up a mass on a spring, like, and suddenly we're dealing with this. So, you know, it's not like we're looking for difficulties, but we want to analyze a mass on a spring. So we get this second order differential equation. Let me say that this here is an example, here below is an example of a first, again, and believe me, again, this all seems like math. It is math. I'm intentionally telling it to you because I want you to know the math that you need to know for the physics, but I also want everybody to know that it's not an assumption that you knew it coming in. Basically, that's the problem with every math class, as far as I'm concerned, that I ever took, is that from day one, I felt behind. In every math class I ever took, it always feels like there's something you're missing. To me, it always felt like I had missed some day when everybody actually got the memo of the basics. And then, sorry, okay, fair question what Rain's asking. So I'm doing exactly what math teachers do. I'm sorry. Rain and everybody, I'm sorry. The question that I'm in is everything I'm talking about right now is all about the very last question of thing on a spring, homework 1. And the very last question, I believe, is question, it's either 6 or 9. Someone will have to tell me. I don't remember the number of the question, but all of what I'm talking about now, and I'm talking a lot, is all about the very, 9, thank you, Robert, okay. question 9 on sheet 1, and it's totally fair that ranges, and I'm glad that she just brought me to. I'm saying a lot about that. Like, we started question 9 2 days ago. We're still in the middle of it, and I'm doing a whole digression now. I mean, it's not really a digression, but I'm doing a whole sidebar right now on math that is now going to pop up for us all in trying to solve question 9 of sheet 1. It's that big of a deal of a question. And it's why, like, I don't, and we will spend this much time if we have to. And it's why everybody gets many chances to do the homework, blah, blah, blah. Because everything we're going to do, I think you'll see, is fair and reasonable. And I'm giving sophisticated titles to, but every thought we make is going to be fair and reasonable, but just would be a lot of thoughts that I need to explain. Okay, so we're on question 9 of sheet 1. Okay, and I'm just like going off and saying a bunch of stuff about it. We haven't gotten an answer yet. By the way, if anybody wants to know, I think the answer does turn out to be 0.116 meters. I think, but I do believe the answer finally to this question will be 0.116 meters. And yeah, the equation that you'll plug in to get that, if anybody's like checking or wanting a reality check, again, fair question on Rain. Thank you, Rain, seriously. But reality check wise, the equation I'm going to try to derive is, you may reckon, is x equals x naught cosine square root of k over mt. Like, so if you did something like that and you got it from the web, good, and you're right. But then you can relax and listen to like me try to explain why that's true. But yeah, that I'm going to try to prove over a lot of discussion where we get this cosine business from, and why, and then when you plug into the cosine, why you get 0.116. Okay, so that's what I'm doing right now. And so let me write, so let me say here, so I'm saying we're trying to get x as a function of t. What we have so far is some physics information that relates x and t in a differential equation sort of way. Yeah, and again, honestly, I don't need to know it's called that in order to solve it, but I am telling everybody, if you follow me in this solution, you will have learned how to do that. Well, here's an example of a first order differential equation. This is an example I'm giving you now. This was not an assignment or anything like that. An example of a first order differential equation would be something like this. Okay, so like that's very similar to the equation I wrote on the other page, right? Like the equation we have to deal with here, the equation that physics is forcing us to deal with, is this. And please do understand, in the history of the world, that's how it goes. Sometimes physics feeds math and sometimes math feeds physics, but like this whole idea that, anyway, that's how it goes. So this is the math that physics is bringing us to. I'm saying, we've got on the left side a derivative there. In fact, we have a second derivative. Yeah, we have a second derivative. So that thing is called a second order differential equation. Before I even deal with it, let me acknowledge to myself, in this next page, there are differential equations in the world that are easier to deal with than that are first order. They would look more, an example would be this one right here. Now, if this were a math class, if we were learning about differential equations in general, we would start with something like this and we build our way up. I really actually think we're going to have to do that right now. But I want to say again, the reason we're backstepping to do that is the physics never said, this equation doesn't say anything about the physical scientific world. Like, I'm making this up as a math thing. Okay, we're going to look at it now, how to solve it in order to solve the actual physics one we have in front of us. And again, this is what physicists do. You can break down stuff that you don't know into little pieces that you do know. So I'm going to say we have this, and I want to solve it for x. I don't know what to do. I have a derivative instead of okay. I want x equals some function of t. I want an equation. Again, the answer I'm looking for is going to be an equation, and then I can plug numbers into it later. It's going to be some equation relating x to t. What I have here is not that. I have an equation relating a derivative of x with respect to t, to x. So I've got x and t involved, but not in the right way. I have a derivative. I want the function. What should I do? If I want to do derivative, I'm going to break everybody up into, hang on a second. I'm going to, because they'll never see this, I'm going to want everybody to do this. And I think some of you did with the homework practice this. Wait, sorry, I'm going to pause for a second. I just asked, did I assign you did I actually post the sheet called mathematical methods and ask you to do it without doing the vector part? Did I do that in this class or did I no, okay, fine, thank you. And I didn't even mention it. Well, either way, okay. I did not. All right, so I'm going to put everybody in breakout rooms in a minute and we're all going to do a math exercise together. I want to make it clear again, it's a math sidebar to get us up to speed with the thing that we have to do for the physics. It's not assuming it's trying to show you the math. So I'm going to put everybody in breakout rooms in a second to do like a sidebar math problem. But it's actually two parts. I'm going to write it down right now on the next page. Okay, I'm going to try to make this as clear as possible. You know, this board does not travel into the breakout rooms. So you have to copy this down before you go into the breakout rooms. And again, I know, and I'm like already like, I know this all seems, it either seems like I'm way off the topic to some of you, or it may seem like, oh my God, there's this much to talk about in one freaking question of one homework assignment. Like, how are we ever going to get through anything? Both those reactions would be fair, but I promise you, it's always like this with the first assignment of this class, and it doesn't always go like this. But there is a lot of math built up that we have to get used to right at the beginning. So what we're all going to do in breakout rooms is try to, in little groups, answer both of these questions, A and B. They're extraordinarily similarly looking questions. They are very similar looking questions, but they will have different answers. Let me also specify one thing that may, okay, for both of these questions, and I hope this is clear, for both of these questions, you're going to assume what you're looking for, what you're trying to get used to is, in both the questions, you're looking for x as a function of t. In both cases, we're assuming that the very first value of x is 0, like just to make things as easy, as straightforward as possible. In both cases, what I just wrote on the side is you're going to assume that the very first value, that x at value t equals 0, equals 0. Now, in the first case, you're being told that the derivative of x with respect to t is equal to some constant times t. In the second case, you're told the exact same thing, except it is equal to some constant times x, okay? And I am saying, also assume that k and m are both constants. Like, they might as well be numbers. In fact, honestly, for any and all of you, if it makes it easier to analyze, to understand this math, like at this stage, if it makes it easier to picture what I'm talking about by like literally plugging in numbers for k and m at 200 and 0.3 and writing that every time, that's completely fine if it makes it easier for you to picture this. Just ultimately realize it's not necessary. But I'm saying what I'm giving you in A is a derivative equals some function of t, and then in B, I'm saying that same derivative equals some function of x. But I'm asking you in both cases, given that information, to find what x is as a function of t. Now, I'm about to put you in breakout rooms and ask you to do your best shot on this, and this will sort of, we will do more, well, anyway, and then we'll talk about it. Again, strangely enough, we need to get our heads around this kind of calculus thinking in order to do math in a spring. By the way, I also know, as a sidebar, I know how much calculus is required to even take physics 1, let alone physics 2. And I know that in physics 1, it seems like we never use it at all. I know all that. And maybe that's true that we never use it all, or maybe we're using it in a weird way that you didn't expect. But here, I can tell you, we totally use it. We really do. We really use not only derivatives, but integrals in a big way in this class. And that is not to scare anybody. My secret enjoyment of this class is that I like to think of this as the place where people actually learn that stuff for the first time, actually. And I hope that will be true for any of you who don't feel confident about integrals and stuff. But we are going to use the crap out of integrals in this class. So here we are going to get on the same page with them. I'm going to tell you right now in both of these questions, and maybe you're so bored that you've already done the answers, I don't know. In both of these questions that I'm giving you in a moment, sure, I'm giving you a derivative and I'm asking for the original function. Like if you're hearing me, you're correct. Like you're trying to give me x as a function of t. All I gave you was dx dt. So if you're thinking to yourself, oh, he gave us a derivative, he wants the function. So I don't want to take a derivative because he already did that. I want to like do a derivative backwards to get what he's looking for. If you're thinking that and you're thinking, so I want to do an antiderivative or an integral, you are right. This is totally about integrals what we're doing. But be careful but do the integral properly, whatever integral you think, because you're going to see from these two examples, if you do it properly, you'll get two different answers. If you jump steps on the integral, you will get the same answer for both, and I don't think that's correct. But yeah, if you're thinking integrals, you're right. Here we go. Welcome to the world of integrals and how they can be subtle. This won't involve fancy integrals. It just involves actually knowing how to set them up or knowing what they mean. So I'm like as nervous as you are about this. I'm going to put you in breakout rooms in a second, but please, like, you're going to do this thing that's written on the board. It won't translate into the rooms electronically. So please jot it down. Am I making any, can I get a show of hands that what I'm asking, like that you get what we're about to do? Okay, that's good enough for me. Thank you, Robert. When I say a show of hands, I mean one thumb. Yes, thank you. Okay, no, okay, we're going to do the, I really do know how to teach. No, really, I have done this before. No, honestly, I swear. And I have used computers before. No, clearly I never have. Also remind me, all of you, if things get really bored, you're allowed it. If things get really boring or dry at any moment, you're also allowed to remind me that I want to practice a poll with you. So if you want to break up, at some point I've got to do that, and it will break up things. So feel free. All right, how many? 3 to 4. Here we go. So please go to your room when assigned. I will not bring this back until at least everybody's in the room. So please go to your rooms. Okay. Isadora, there, good. Isadora, let's see. Isadora, you good? Can you hear? Brianna, can you hear? You good? So we want to go to the breakout rooms. Great, thank you very much. Okay, great, thank you. All right, awesome. Okay. Hi. Okay. Hello. Hello. Okay. Okay. Are we all that? No. Ah. Some people know. Oh, okay. Sorry. Okay, I think so. Can you guys hear me? Oh, can you hear me? Oh, wait. Oh, yes. Oh, thank you. Okay, I totally appreciate. God, I swear, you. You know, you totally. Yeah. It's in. Well, all the yet. Oh, there was no. Oh. Okay, I totally appreciate that. I am sorry. No, I'm amazed. Okay. Oh, well, wait a minute. That's really good to hear. I mean, it's not good to hear. No, I apologize. I'm responding to the chat. Okay. This feels very human to me. I was just about to praise you guys for like just the simple yeses that you give me in the chat when I ask if you hear me. Like it really does make a difference. But that thank you for telling me. I'm always so nervous. I mean, I know people have mixed feelings about the breakout rooms. I'm always so nervous that they're falling apart and that people are frustrated, or that you'll think I've just like walked away, that I bring you back. No, if you want more time, let me, unless there's real objection, if you're saying there's not enough time, I absolutely want to put you back. No, and that's fair. Hold on a second. I always sound like I'm in a rush because I'm always in a rush because I'm always behind because I don't manage my time well, and I always feel rushed. But and I know that me sounding rushed can rush other people. No, I do not want people to be rushed. I would rather. I literally, for up to me, we spent a whole semester on one homework assignment if necessary, if it actually meant that everybody was thinking about it the whole time and getting smarter as a result. So no. If you guys need more time, I don't want to say a word. If you feel like you were in thought and getting, I mean, if you feel like you hit a wall, then I'll talk. But no, if you want, wait a second. No, and this is good.
Can
Oh,
we
and I
like
can.
can we
Yeah.
skip the breakout rooms? Because I went back to my calculus notes and like I found stuff, but I didn't really know how to apply it to the equations that you gave us. And I don't think like the breakout rooms will help us figure out how to apply what we learned in calculus to this. Like,
Fair enough. Oh, sorry. Keep talking.
yeah, I would much rather you explain it.
Well, that's fine too. No, I'm happy to. I mean, all right. Sure. Is that? Wait, let me just retweet. Okay. Wait. First of all, I'm delighted. Like, really. Um, there's certain things I'm so bad at, but one thing, it's hard to trust me. If I knew exactly what everybody wanted right now, like whether it was for me to explain it or to go back with more time or for me to give it, I would do whatever it was that people want. So I'm happy. If you want me to explain, I'm happy to explain. Um, I wait, but now I'm like, I feel like people want different things. But yeah, how about I'll start? Well, I will start. But no, when you guys tell me that it wasn't enough time, I think what I'll have to figure out at some point, maybe I'll take a poll, is like for some people that means they need more time in the breakout room. Other people are saying maybe, and maybe this is what Rain's saying, if you guys are saying you just need more time to think, like you don't want to be in these like crazy rooms, but you want to think, or you want me to give a hint and you want to think, I will always respect that. Like as long as I know that that's true, I'm happy to shut the heck up and just let people think for a half hour. Even, and let me say this really seriously to everybody again, because I'm having a hard time with this like doing all this from home in the middle of my home thing. So I know the minute I leave this class, and when I'm not in the middle of this hour and 15 minutes, it's extremely hard to get my attention and sustain it. It's hard for me to get my own attention and sustain it when I'm now here is at least a safe zone where we can do what we want as long as we're here for an hour and 15 minutes. And I really want you guys to know, if I sometimes have to act like it's the only hour and 15 minutes, this and another one, that you have all week to think about physics, like for me too. So what I'm saying very seriously is, if the more you guys are honest to each other, even in private, so that you can then be honest to me of exactly what we need to be doing to actually be getting smarter about physics, I am game. Like I would sit here for an hour and 15 minutes and let just everybody think for an hour and 15 minutes, if on a thing, if that's what people wanted, as long as that's what people wanted. But of course, people want different things, so we got to figure it out. But let me look in the thing. Oh, well, I could do that. Yeah, I could do that. I can even say, Yeah. Wait, can I do that? Wait, let me do one thing about that is I tried to do a poll yesterday in a different class and it ended up being a total disaster. Something didn't work about the poll for so long that I do need to practice doing polls with you. But I have a feeling if this is the important poll that we need, like right now, it's going to bust up and not work because I'm still not doing the polls right. So let me try this because I do think this is important because again, I have really strong feelings about how people need time to actually think. I mean, to put it, and that we never spend enough time in class just being able to quietly think because there isn't time because we're trying to cover material. But like I know for many people, there's no other opportunity in the whole day to actually think, or and also no reason to care. So let me say this. This is what I'm going to do. I'm going to turn off, I'm going to put down my earphones and I'm going to walk away and my mute and everything. I'm going to leave this on for everybody. I'm going to walk out of the room and it's not bullshitting. I'm going to walk out of the room for like 3 minutes and let you all talk about this however, and just decide like what my best next move is, whether it's to give a hint and then let some of you not listen or what. Like, I don't care if different people end up doing different things, but I might not be able to actually arrange it electronically that easily. So, but again, no, I feel strongly also that if there's a chance that anybody ever learns calculus ever, it's actually through physics, not before. I know you're required to take it for physics, but I think all that is nonsense. I think you could just as easily be required to take physics in order to take calc. And I swear to all of you, I love physics and I now love calculus, but I did not start off by having any interest in calculus or loving it at all. I got it through the physics and I eventually got to see why it was so exciting that I wanted more of it, like personally. But I am viewing this as my chance to teach you guys things that you that might just get away with skipping around or not caring about. So I want to do it whatever way actually works with you. It is not an assumption that you already know this math or that you already block, but it is an assumption we're going to get it. So I'm going to walk away for 3 minutes, literally, and you guys like decide what my best move is to do this problem or not or whatever. You'll also see that I just assigned 2 homeworks, one for next Tuesday and one for next Thursday on all of this stuff. Like, so there's homework already in the queue to get us all up to speed with math, but the idea is for us all together to get to the same place with math. It's not to pretend that we're already there. So, okay, I'm gonna walk, I'm putting on my earphones, I'm putting on mute, I'm walking away. I'll give you like 4 or 5.
Did anyone actually start like figuring out how to do the problem?
Nope.
We thought about it.
Warning, I'm coming back. Still can't hear, but do you want more time to talk? Oh, I don't know if you can hear me actually, but do you want more time to talk amongst yourselves? I'm intentionally not looking at the chat yet. I mean, should I look at the chat? Should I come in? Should I stay out? You guys tell me.
I think we're just confused. Like from what I'm seeing, most of us don't get it or didn't have enough time to like really think about it.
Fair enough, fair enough, fair enough. Okay. Totally fair. Okay, no, totally fair. Okay, and I'm looking at the chat. All right, so it sounds like, I mean, so I will just start talking then if that's if that's okay. I mean, I'll start trying to explain it if that's, oh, wait, let me see, wait.
Yeah.
Okay, no, and I'm happy to. Again, believe me, I'm happy. Also, if nothing else, I just know I'd rather talk thinking that I'm clarifying something that people need than that I'm just talking to myself or whatever. So I'm happy to talk about it. One thing that, and why, I'll tell you the first reason that this math looks weird. Like I'm glad someone did. And I'm totally, again, this is where I appreciate, like, I feel like, not to be weird, but I feel like Rain deserves an A just for like speaking about this stuff the way she's, and you all like that, none of us can get educated or educate anybody without like being just this honest about where our minds are. And nobody actually ever knows where anybody's minds is without this kind of talk. So one thing is, I bet that all this math does look like math that's in people's notebooks from old classes. Like anybody who, I'm sure you would see the stuff, but I'm also equally sure that even looking in your old books, it wouldn't be clear what to do right away. Because what I think is, and this is what happened to me, I imagine that to many of you, it's not even clear exactly what question I'm asking right now, like what it is that I'm asking, even though I am asking something fair, but it is weird what I'm asking. I'm asking to, I mean, it's very fair because it comes up all the time, but what I'm asking is for us to work backwards and get x as a function of t, assuming that we know something about its derivative. So I will right now. So, and I think partly what's making it look difficult is that in that parentheses, I keep writing k over m. I do want everybody, and I keep saying that k and m are each numbers, but let me go a step further and tell everybody, you know, k is some number, m is some other number. A number divided by a number, this is just quick, a number divided by a number is still like some number. So one thing is, I'm writing k over m because that's what the physics says, but I could just write that whole thing as like the letter a, or the number 5 or something. And that would start making this look a little bit less, It already looks confusing because there's so many damn letters in it. And there's so many letters because that's the reality of the physics. But if you're looking at an old math notebook, right, you would never find something that had a K and an M like that. There'd be no reason. By the way, I'm totally, my board just lost its connection. It's coming back, I'm sorry. Okay, here we go. But so there's many reasons why this looks like an out of nowhere question, but going back to where the board was, sorry, coming back. Okay, I will show you. I'll start doing what I would do. This is, we have, all right, so this is me starting to solve it now. Like the first question was, I'm just rewriting the question here. What's given is dx over dt, like the derivative of x with respect to t, equals negative k over m times t. Like that's a given. Also, what is given is that k and m are constants, and the x sub 0, like x, when, like in other words, when what's also given is one particular value of x, that when t equals 0, x equals 0. That's supposed to be given. Now, our goal is to determine x equal f of t. Here's the first step I do, which it is always what people need. Like most people don't know how to start or what the first step is. The key first step that most people wouldn't think of is I'm going to multiply both sides by dt. It sounds completely obvious after I say it, I know, but it's totally not obvious for 1,000 reasons. But the first thing I'm going to do is what I wrote here at the bottom of the sheet. I'm going to multiply both sides by dt. Okay, dx over dt is a derivative, right? But it is a fraction. I mean, I'll get back to that. In other words, you can do this. You can do this. There are rare cases where you can't. And there's like if you want to be a mathematical purist, like there's reasons you have to prove like why in general you can do this. But the fact is, you all know that you could do this with regular fractions. It might not have occurred to you that you could do this with the sort of fraction that a derivative is. But partly I'm here as a physicist to tell you a derivative is a fraction. A derivative is a ratio. It just happens to be a ratio of infinitely small quantities. I'll get back to that, but anyway, it's a ratio. So you can multiply both sides by dt. And it turns out to be really useful to do that because if you multiply both sides by dt, because that's what I'm doing on the bottom step here, that is my first step to solving this. Then what I can say is, oh, hold on, there's a D thing going on the left side. There's a D thing going on the right-hand side. So I can integrate both sides. I can do an antiderivative, right? In other words, I'm gonna write this down. I can, because I'm now saying D, and of course, like everything else, if you get what I'm saying, you might then go, oh, that's all, like, oh my God, why didn't I think of that? Or why didn't he just say that before? But no, there's a reason that we might not have thought of it, but it is true when I'm, oops, sorry, that's not what I meant to do. Okay, so I have this, so I'm going to integrate both sides. Okay, now I don't know what values to put on that integral or anything. I just know, like, why am I allowed to integrate one side? Because I'm allowed to do whatever I want to one side as long as I do the same thing to the other. Why do I want to? Because I see a dx there, like, because you all know what integrals look like. Integrals always have that sign, and they always have a d something term in it. I know if you're like me, that term that's sitting there in the integral thing just like annoyed you or just like sat there forever. Like, and I'll try to explain why it's really there, but well, all of this will hopefully ultimately show you why it's really there, what it means. But the fact is, you know, you never have in a math class, like sidebar, no one ever walks up to you in a math class and says, like, what's the integral of 5? Like that, right? They might say, what's the integral of 5 dx? That they might, or they might say, what's the integral of x dx? Or even some letter a dx, or they might say, what's the integral of y squared dy? But there's always like that d thing sitting there, right? They don't ever do this. Similarly, by the way, you never see in a math class, you never see like, what's the integral of y times dx over dy? Like, what? No, that's crazy town. I don't know what you get used to. And I know for many of us, it's just a matter of getting used, but, and I will explain, but what you know is whenever you have an integral, it's always the integral of some d thing. Because secretly what it means is you're taking the continuous sum of an infinite number of infinitesimal pieces. But I'll get back to that. But anyway, I'm saying we now have a proper expression of the integral of dx. Like, we literally have the integral of dx equals the integral of, sorry, t. Right now that may look, I'm going to go on to the next page just because it's all sloppy here. So yeah, well, here, I'll just write it again. Just yeah, I want to just go to the, tell me if you want me to go back, but I'm going to go to the next page just because this is getting sloppy and I want to write this very clearly. But I'm saying what we have so far is this. Okay, now I don't know anything about limits of the integral or anything like that. I just know I integrated both sides. So it looks like indefinite integrals to me right now. This looks like but that's okay. Like, you guys know, maybe this is review, but you've seen indefinite integrals before. And maybe, I don't know if this looks complicated or not, but let's just deal with it side by side. Like on the left side, we have integral of dx. Maybe that's so simple, it looks hard, but it might look less hard to many of you if we just realize that's just the same thing as saying integral of 1 times dx. I don't know if that makes it harder or easier, but I think we actually know what that is. If someone walked up to you in a math class and said, what's the integral of dx? What they're really asking is, what do you get when you take a whole bunch of little x intervals and add them all up together? What you get is one big x interval. In other words, I'm just going to cut to the chase and say the integral of dx is x, right? Or put another way, the integral of 1, if you do the power rule, right? You have to raise x, 1 is the same thing as x to the 0, right? So the integral of x to the 0 dx, right, is x over 1, right? I don't know if you do the power rule. If you remember any integrals, the integral of dx is simply x, but it's an indefinite integral. So I do have to say something like plus c. That may be familiar enough. So I'm saying the left side of this, the left side of what I have is simply x plus c. Are we together so far? But this is where integrals are coming in. Well, integrals are coming in because I see a dx on the left side and I see a dt. And they're also coming in because I've been given a derivative, but I want to work backwards from that derivative. I want to work to the function. So in effect, I am taking antiderivatives. But I just did the left side. Now the right side. Maybe I'll give everybody well, I'll give one more hint and I'll pause and have you, the right side might look complicated. You don't literally see it written on any sheet of paper in any math notes from any class probably, but yes, you do really, if you realize that the K and the M are just like themselves numbers, and so is negative sign. A negative sign is just like the number -1. In other words, I'm saying those are all constants. They can come out of the integral. So I had on the right side, I have those constants times, and I'm going to, pardon me, I hope it's not bad if I do that. I'll try to write that again, but I just want to keep this clear. So I have this so far. And again, please stop me if it, but this is what I think I have so far. And now so the left side is still x plus c. And the right side is -km times something. I'm going to give you does anybody want to tell me just to see what, like, I think you're probably in a position to do the right side now that you see what I'm doing. It's power rule again. What's the, yes, thank you. Exactly. Awesome. Right. Exactly. Hold on, let me just get the, yes. In other words, right. Yeah. The integral of t dt is t squared over 2, and then plus some constant, like this is also an indefinite integral, right? So there's going to be some constant here too. I don't know that it's necessary. Oh, oh, funny. Yeah, wow. He is a fast, yeah, that is true. He is fast. And LOL indeed. Oh, I'm still cracking up when someone before in the chat said retweet. I cannot even explain how funny I think that is. Partly I think that's funny because it's funny to me that I even get that. And if you ever any Twitter, Yaverbaum on Twitter, that's my brother. That's not me. If you do Twitter, I've never done. But anyway, there's going to be a constant here, and there's no reason to assume it's the same constant as on the other side. So I'll call it like C sub 2 if you like, and I could even like retroactively rename the other one C1 if that makes sense. It looks like things are getting more complicated, but we're actually almost done. They're really not that complicated at all. What do we have so far? We have x plus C1 equals negative kt squared over 2m, like if you want, you can write it that way, or like -1/2 k over m, whatever, t squared plus C2. Now, what was oh, sorry, where did C2? Well, that's a great question, and thank you it came from the fact that the integral on the right-hand side is an indefinite integral, just like the integral on the left-hand side was an indefinite integral. So I'll write this down in a second, but any indefinite integral I see always has an arbitrary constant at the end. In other words, so I could have just called it C, but since I already had a constant on the left-hand side called C, I don't want to believe that they're the same number necessarily. So I gave them two different. So what I'm saying is this. I think that's a great question. I forget who just asked in the chat, but so I can go back to that page in a second, but I'm saying we did the left-hand side and we said this in effect. And then we're saying on the right-hand side, oh, sorry, what was that? The left-hand, sorry. And on the right-hand side, we said, on the right-hand side, we had, right. I'm basically saying that the left-hand side and the right-hand side are each separate integrals that can be evaluated or that can be solved on their own. But each one, since it's an indefinite integral, each one pops out an answer that has an arbitrary constant in it because there were no limits placed on the integration. Does that, I don't know. I think it's a really good question, but I don't know if I'm answering it or not. Is it, oh, yes. Okay, cool. Thank you. Okay. So, thank you. No, great. And I'm glad that someone stopped me on that because now I'm going to do something with those C1s. Like it suddenly looks like we're getting all this crap that we do. Pardon my language. We're looking for x as a function of t, and we'll know we have an answer when we have something where you can plug in t and do a bunch of things with K and M. Like K and M can be in our answer because they're known constants. They can be in our answer, but anything else that's not known can't be in our answer. So I'm not done yet. What I'm saying right now, what we have so far is x plus C1 equals negative K over 2M. And that's just a habit of, I try to collect all the constants and sort of keep them all together and focus my attention always on the variables. So this is what we have so far, okay? What we're looking for is x as a function of t. So I want to isolate x. So I'm almost there, right? I'm going to subtract C1 from both sides. So I'll say I'm isolating the x, so I get so I have this, right? Now C1 and C2 are each arbitrary constants. They're constants in just like K and M, like they are a number that won't change. That's the good news. The bad news is, unlike K and M, I don't know what they are. They each stand for a number that I don't know what it is. Because no one told me like the limits of my integration, and they're each a different number, or at least I have no reason to assume that they would be the same. So I had to give them each a different name. It's two unknown things. So that's a little bit problematic. Like we're trying to get down here, like we're not trying to generate more unknowns. So the first thing I want to say that we do a lot in physics that you, and again, it's totally, you'll see what I'm about to do is mathematically completely reasonable, but you may not have had occasion to do it before. Like on this right-hand side, I've got these two unknowns, C1 and C2, but each one of them is an unknown, like arbitrary number. It's some number that I don't know, each one of them. And it's two separate numbers. But here's the thing, since I don't know them, some unknown number minus some unknown other number will give me some third unknown number. So I actually, what I'm saying is a very important trick that a very important technique that we do in physics to solve things like this is like, so I'm going to start the next page. I'm just going to recopy. Okay, I'm just recopying the last line first. So, and then I'm going to do something. So the last line was this. Right? So I'm going to say this. I'm going to say, let C3 be the name of what you get when you subtract C2 from C1. What you subtract some unknown number that I don't know that is there, minus some other number that I don't know but is there. What I'm going to get is some third unknown number. So why don't I just I'm going to call C1 minus C2, I'm going to call it C3. And by that, literally reduce the number of unknown things I have to worry about down to one. And then since there's only, since now I'll just have just C3 in the expression, this is like a really weird trick that this works in a way, then I'm going to say, well, there's only C3 sitting there. Then I'm going to just call it C. Like this looks like total, like, so what I'm saying is what we so far have is then X equals okay, now I'm still not done. I'm almost done. Like in a way I'm done. What am I looking for? I'm looking for X as a function of T. Now that is what I have here. I do have X as a function of T. I have a rule here that if you plugged in T, it tells me, okay, then square that T and then multiply it by K, which is a number that we all assume that we know, even if it like, you know, assume that it's a given number, like you measured in the lab. It just might be different when we do it tomorrow or something, but take your T squared, multiply by that known K, divide by 2, divide by the known M, multiply by -1, okay? And then add the number C to it, and that will give you X. We are there, we have what we want, except for one thing, the C is still unknown. Okay, we're almost there, but I just have to be clear. We now have letters doing, like this is where math actually becomes math or where physics actually becomes physics. Like the hard part here is not computations, calculators won't help us. The hard part is like I have a bunch of letters here in this statement that are all functioning in different ways. I have a dependent, in fact, I want to write this down. Forgive me if this is, but I'm saying literally here, this X is the dependent variable. Okay, this T over here is the independent variable. this K and this M are each like known constants. They don't look known, but they are. They're like given at the beginning of the problem, known constants. Technically, the word for that is parameters. We'll get to that, but those are known. And then this C is an unknown constant. They just all look like letters, and they did to me for years, but they're all actually serving a very different purpose in the statement. And it unknown constant. And why am I making this identification is if I could just get a value for C, then I would say I have an answer. Like this is a new type of question, but I have to keep in mind what the type of answer is I'm looking for. I'm looking for X as a function of T, which means a rule that you would put T in and it would spit out X. But that rule will only work if like I know all the reference in that rule. Right now, the one thing that is unknown is C because it just popped out from my calculations. It was never given, it just popped out from integration. So what can I do? I can cry. I can look at, oh my God, and I can wrap up in 2 minutes, but guess what? We're gonna get there. And the first thing you're gonna do, I'm gonna get the answer in 1 second. Like, I know we have 2 minutes. I'm gonna get the answer to this. I promise you, if you do the exact same thing I did here, you'll be able to get the answer to the other one. And please do that first for homework, like wherever you are in the homework. I'm gonna say, I won't hold you late. But first thing to try to do the homework is the other question, just follow this exact procedure, but just be careful. And it'll be 1 step harder and you'll get a different answer, but do follow this procedure of like, but anyway, we're almost there. I just need to solve for X. Excuse me, I just need to solve for C. Can I possibly do it? Yes. And again, this is the last thing. And of course, if you have to go like right now, then go. And this recording will be posted and all that stuff. And then what your homework is after this. But wherever you are in the homework, just catch yourself up. But please do this, the other part of this first. And when we meet next time, we'll first find out what you guys want. Like I won't start by talking. I'll start by, because I like this class. I like what's going on here in that way. So to solve for C, let's remember the one other piece of information that was given that we haven't used yet. The one other piece of information that was ever given is that X at value 0 equals 0. Like we were told, however you put it, X sub naught, however you put it, when T equals 0, X equals 0. This was a given piece of information. I had to give it for exactly this reason, but I did give it. So therefore, what does that mean? It means thus we have one special case we can plug into our equation and therefore solve for the last unknown. Thus, because our equation right now, right, was X equals, and we're just about done, I promise, negative K over 2m T squared plus C. Well, that's what we're solving for. We're trying to get rid of the C, but we know, oh yeah, when T is 0, X is 0. What we were given, when T is 0, we know X is supposed to be 0. So we know 0 must equal like negative 0 plus C. 0, like literally we know from the one case that 0 has to equal 0 plus C. So in other words, 0 equals C. Which doesn't mean the C doesn't exist. It means it equals 0. It means we looked at the special easiest case possible. It's like, in other words, C doesn't always have to equal 0, but we said I happen to have set it up here so that C equals 0. Therefore, we have our answer. Our answer is X equals negative K over 2m T squared. That's the answer to the first question, like if dx over dt equals negative K over m T, this is the answer. Now you all are going to do the same thing, but just be careful. Like understand you can only integrate something when it has a d blah in it. You can't integrate y, you can integrate dy, or you can integrate y dy or y squared dy, but you can't integrate y, you can integrate dy. Also, you cannot integrate dy over dx. You could just integrate d things. So just take whatever equation I gave you and just rearrange until you have d things and then integrate and see and follow this procedure. And then go back and see if any of this helps you with homework 1. Like if you're totally hit the wall with homework 1, move on to homework 2 that I just assigned, blah, blah, blah. I think everybody gets it, but I mean, I don't think everybody gets all the math, but I think everybody gets what I'm saying for the moment. Like, well, this is the answer to the first exercise. For what it's worth, the answer to the second you know, do I want to do it? No, I want to hear from you guys. It's going to be different. It's not a t squared. It'll have like an e to the or something in the answer. It will. It'll have like an e to the or a logarithm or something weird if you do it right. But but thank you guys again for being so participatory. Or if you're good, I'm good. And I will start in office hours at some point. I will, I promise. But yeah, we're good. We're good. Okay. All right. So I think I'm saying, okay. Thank you very much, guys. I'm literally going to end.